Welcome to EE331 Lesson 17, Inductor Transients. Inductor transient analysis follows the same procedure as those for capacitors, but this time we solve for inductor current. Also, the time constant will be redefined for an inductor circuit. Solving inductor transient current as a function of time requires 4 steps and 3 circuit drawings. We'll explain the steps using the circuit below. At t is equal to 0, the switch closes and the source is connected to the right part of the circuit. The current through the inductor will reach steady state after 5 time constants, and the plot will look something like this. We'll follow the steps below to determine the final current through the inductor and tau. Step 1. Redraw the original circuit in its initial state under DC steady state conditions. This drawing will be a modification of the original circuit. Remember, DC steady state means we treat inductors as short circuits. Calculate inductor current in your modified circuit drawing. This current is the initial current. Note that there's no sources connected, so IL is equal to 0. Step 2. Redraw the original circuit in its final state under DC steady state conditions. This drawing will be a modification of the original circuit. Calculate the inductor current in your second circuit drawing. This current is the final current. In the circuit to the right, we've shorted the capacitor, so we can easily find the current through this branch by taking 5 volts and dividing it by 20 ohms. Step 3. Redraw the original circuit after the key event with the inductor removed and the sources turned to 0. This procedure is identical to calculating R Thevenin, except the inductor is now the load. Examining the circuit to the right, we need to travel from node A to node B and then figure out what the Thevenin resistance is. The first thing we bump into is a 20 ohm resistor, and then we're going to bypass the 10 ohm resistor and go to node B because this has 0 resistance. Now we can figure out our time constant, which in this case is L divided by R Thevenin. Tau is equal to 50 microseconds, so we know that the circuit changes state in 250 microseconds. IL as a function of time is 0.25 minus 0.25 e to the minus t over 50 microseconds for t greater than 0. Notice how for the inductor the time constant tau is equal to L over R Thevenin. This is different than the time constant for the capacitor circuit, which was R Thevenin times C. Be careful because the equation may seem backwards. However, in both the capacitor and inductor equations, the exponential term has the form e to the minus t over tau. Let's recap the steps for finding the inductor current as a function of time. First, we redraw the circuit in its original state and find the initial DC inductor current. Second, we draw the circuit in the final state and we find the final DC inductor current. Third, in the final state, we turn off the sources, remove the inductor, and calculate the Thevenin resistance. And then fourth, we substitute our answers into the equation. In practice problem 1, the switch has been open for a long time and then is closed at t equal to 0. Write the equation for the inductor current as a function of time. And then calculate the energy stored in the inductor at 1.6 milliseconds. We can solve for the final current using nodal analysis, but instead let's reduce the circuit, find the source current, and then do a current divider. The current through the inductor in the final state is 600 milliamps. Now let's turn off our source, remove our inductor, and find R Thevenin. We begin at the top node, and the first thing we bump into is an 8 ohm resistor. Then we note that 3 and 6 ohms are in parallel as we return to the second node. Now let's find tau. Tau is equal to 400 microseconds. 5 tau is 2 milliseconds. So the current goes from 0 to 600 milliamps in 2 milliseconds. Now let's plug our values into our equation. IL as a function of time is 600 minus 600 e to the minus t over 400 microseconds, milliamps, t greater than 0. To find the energy stored in the inductor when time is equal to 1.6 milliseconds, we'll use the equation 1/2 Li squared, and then we'll plug 1.6 milliseconds in for t and solve this equation. Turns out the energy stored in the inductor's magnetic field at t equals to 1.6 milliseconds is 693.87 microjoules. Note that the current comes out to be 589, which is very close to 600 milliamps because the time 1.6 milliseconds is close to 5 tau. If you're asked for inductor voltage VL as a function of time, then first calculate the current using the process above. Then apply the inductor law, which says the voltage of the inductor is equal to L times di dt. To find the derivative of an exponent, use the process shown here. Remember how we called the capacitor the voltage keeper-upper? Well, inductors are current keeper-uppers. The current cannot change instantaneously, but needs 5 tau to go from its initial state to its final state. However, the voltage can change instantaneously, and does so as shown in this plot. In practice problem number 2, the switch has been closed for a long time and then opened at t equals to 0. We need to write and plot the equations for the inductor voltage and current as a function of time, and then tell how long it will take for the inductor current to be considered negligible. We draw the circuit in the initial state and note that the 100 ohm resistor is shorted out by the inductor in DC steady state, so we can ignore the 100 ohm resistor. What we're really after is how much of the source current goes down this branch. We can find that out using a current divider. 0.5 amps times the quantity, 20 ohms, in parallel with 10 plus 20 ohms. This is our equivalent resistance. In the bottom goes the total resistance in the branch current that we're looking for. The initial current comes out to be 200 milliamps. Now let's remove the inductor and find the Thevenin resistance. Our Thevenin in this case is 100 ohms. Tau comes out to be 20 microseconds and 5 tau is 100 microseconds. So the circuit will go from an initial state of 200 milliamps through the inductor to 0 milliamps through the inductor in 100 microseconds. Let's write the equation. The current through the inductor as a function of time is 200 milliamps e to the minus t over 20 microseconds for t greater than 0. Now we can find the voltage across the inductor by taking the derivative and multiplying it by L. VL as a function of time is negative 20 e to the minus t over 20 microseconds. The unit is volts and is for time greater than 0. For our last problem, the circuit below is the same as the one in problem 2. However, the inductor current decay is interrupted by closing the switch again at t equal to 2 tau. Write the new equations for current and voltage as a function of time, treating t equal to 2 tau as the new t equal to 0. Finally, plot the equations from practice problem 2 and practice problem 3 on the same graph. We can take our previous equation, calculate I at 2 tau to come up with the initial current for our new circuit. That gives us 27.07 milliamps. Now let's draw the circuit in its final state to find the final current through the inductor. Again, we have the scenario where the 100 ohm resistor is shorted out by this branch, so we can ignore it. We still have the work from our current divider that we did in the previous problem to know the current through this branch, which is 200 milliamps. Now we'll redraw the circuit, turn off the source, remove our inductor, and find our Thevenin. Our Thevenin in this case comes out to be 33.3 ohms. Now we can find tau. Tau is equal to 60 microseconds. 5 tau is equal to 300 microseconds. So it takes 300 microseconds to go from an initial current of 27.07 milliamps to 200 milliamps in this new condition. Let's write our equation for I and V. IL as a function of t is 200 minus 172.93 e to the minus t over 60 microseconds. This is in milliamps for t greater than 0. The voltage is found by taking the derivative of the current, multiplying it by L, which is 5.76 e to the minus t over 60 microseconds volts for t greater than 0. Now we can plot the graphs. For the current plot, the initial current through the inductor was 200 milliamps before the switch was flipped. When the source was disconnected, it degraded down to 27 milliamps. It took about 2 time constants to get there. Then the switch was closed again and the source was reconnected. Over 5 time constants, it built back up to 200 milliamps. But this process was slower than this process because the new time constant was 60 microseconds. For the voltage plot, it was initially at 0 before dropping to a negative 20 volts. It gradually increased to negative 2.7 volts before jumping up to 5.76 volts when the switch was closed. Eventually, it degraded back down to 0 at 340 microseconds.